Hello friends, welcome to the channel Physics by IITians.
Hello, friends. Welcome to the channel Physics by IITians, where we learn and understand physics to crack interviews and PhD related exams. So, before starting this video, I would like to say sorry for not being active in YouTube and taking a long pause. So, that I am really sorry for that. But from today onwards, we will try to make sure that we will regularly upload very important physics videos so that it could be helpful, very helpful to for clear your concepts and physics related, any kind of basic physics related concepts. So this video is very helpful to understand why the Nobel Prize of Physics for 2025 has been awarded. And I would like to emphasize on the physical aspect and physical meaning of the uh, key concept that has been awarded for the prize. So you all may know that this year Nobel Prize in Physics 2025 was awarded jointly to John Clark, Michael H. Deverett, and John M. Martinez for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. So this is a huge keywords like macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. What is that and why it got a Nobel Prize, such as prestigious award? So this Nobel Prize laureates in physics for 2025, they have done performed a series of experiments to demonstrate the bizarre properties of the quantum world, which can be made concrete in a system big enough to be held in the hand. So, what does it mean? So, we know that quantum mechanics, especially, it is applied in the microscopic world. But the question is that do macroscopic variables obey quantum mechanics? So, if we know about the Schrodinger cat experiment, we know that Schrodinger's cat collapses to classical states because quantum mechanics is not allowed on macroscopic objects. Because, according to Schrodinger, this experiment is like the cat can become alive at the same moment it can be also dead, and the probability of cat being alive and being dead is 50%, which is not physically permissible. So that's why this kind of concept, we only think that this is only absolutely applicable for the microscopic object, and it is not valid for the macroscopic world, and macroscopic world is ruled by the classical mechanics. But there is a question that do we observe quantum mechanical phenomena in macroscopic scale? Yes. For example, superconductor. Then, does this macroscopic object show quantum mechanics? That is also yes, because it's a macroscopic quantum computation is an example where macroscopic objects show quantum mechanics. So, this year, the Nobel Prize, which is established, that is established to show that the macroscopic world, which is our world, can also show quantum mechanics. And based on this, they have awarded for the discovery of macroscopic quantum mechanical tunneling. So, what is the quantum tunneling effect? So, all we know that quantum tunneling is a quantum mechanical phenomena where a particle can pass through a potential energy barrier even if it does not have enough energy to overcome it classically. So, for example, if we have a particle barrier of, let's say, Vx, and the energy of the particle, which is now represented by a wave package, it is less than the potential barrier, that is Vx. Even if it is less than the barrier, there is absolute probability of tunneling the particle through the barrier, and it cannot be zero. So there is always a finite probability to pass the barrier, which is classically, it is not permissible that a particle having less energy than the barrier, kind of potential barrier, it cannot overcome the potential barrier. So for example, there is a ball I'm throwing to a wall. And I know if I throw the ball to the wall, towards the wall, it will come back to me because the ball does not have that particular energy to penetrate through the wall. But quantum mechanically, there is a finite probability, and that depends on the strength of the potential barrier of the wall and its width of the potential. And there is a finite quantum tunneling probability, which this is transmission probability. And for example, we know that we have a alpha particle emission from the nucleus, and it can overcome the alpha particle can come throughout the barrier of the Coulombic barrier of the nucleus, and we get the alpha particle radiation. So it is a quantum tunneling phenomena which can be observable in real world. So now you have to understand what is this macroscopic quantum tunneling, because all the tunneling we have already discussed, that is microscopic, because we are talking about alpha particle, we are talking about nucleus, we are talking about electrons, which are microscopic. So how this can be macroscopic? So what do you mean by macroscopic quantum mechanical tunneling? So let's say microscope. What does it mean by macroscopy? Is that the quantum effect which is observed in a system that is large enough. That means that involves many particles, or in fact, it can involve a device which could physically hold just not a single atom or just not a single electron. And what is energy quantization? So we know that in quantum mechanics, the particles can have only discrete energy levels. For example, we have a particle in a box, and if these are like classical mechanical particle, they obey classical mechanics, then they could have any amount of energy, any arbitrary amount of energy or continuous amount of energy. But if a particle which is quantum mechanically, it is confined in a box, it could only have certain quantized energy level, and these energy eigenvalues can be represented by certain discrete levels, which can be n equal n, and n can be from like n can only take integer values. So this we know. So this is named as energy quantization, and this phenomenon is also available, we know, from the hydrogen atom, for the molecules, for the vibrations of molecules. So each of them can be expressed in terms of quantized energy, each of the energy levels. And what is the electric circuit? So in a superconducting circuit, if we use Josephson junction, which I will tell you in some slides, which is just after some slides. So this could be done that this electric circuit could show energy quantization, and which is a quantum mechanical phenomena. So the electric circuit, we know, in the daily life, it is a macroscopic phenomena, and this macroscopic phenomena, like the electric circuit, which is a macroscopic dimension, can show energy quantization, which is a quantum mechanical concept. So how is this possible? So it is possible by Josephson junction plus the superconductivity concept. So we can make separate videos on superconductors. Here I just only tell you what is superconductor. You may all know that superconductors are materials which conduct electricity without any resistance at very low temperature. And what is Josephson junction? This is made by placing very thin insulating barrier between two superconductors. So let's say we have a metal, we have another metal, and we have two, or we can have two superconductors, and in between we have an insulator. So then in such a scenario where we have two superconductors and they have an insulating barrier, and what will happen then? So if we build the circuit and we fabricate the superconducting Josephson junction circuit that I have already told, that two superconductors are connected by an insulator, that means that thin insulator is sandwiched between the two superconductors. And if we keep the circuit inside a very low temperature, what will happen? So for the superconductor, we know there is a formation of Cooper pair, where the electrons are actually pairing with each other instead of repulsing with each other, which is very common for uh, electrons. They are negatively charged, so they usually repel each other. But inside a superconductor, uh, if we see what is happening, so there is a Cooper pair formation is happening, and this Cooper pair actually they are trying to make a macroscopic phenomena, and they don't repel with each other. That means that in a normal conductor, electrons usually repel with each other and it causes finite resistance or heat losses in the circuit. But when the material becomes a superconductor, the electrons will jump as pairs, and these are known as Cooper pairs, and form a current where there is no resistance. And this gap of the two superconductors are in between a dielectric gap, which could be like vacuum as well. So this whole thing is as a Josephson junction. And now, if these super pairs, they can behave as a single particle because they are not uh, repelling with each other, but they are pairing with each other. So they can make as a macroscopic state, just like a Bose-Einstein state. So they all macroscopically link with each other, and they can create and they can be described by a single macroscopic state or single wave function. So what happens if we do the same thing with the Cooper pair and we will decrease the temperature? So let's say it's not due to the quantum tunneling and the thermal activation is there, like in the Josephson junction, we have a thermal activation, means we have a finite thermal energy in the circuit, and we don't see any kind of temperature fluctuation, any kind of voltage fluctuation, which is instant due to the activation. But let's say we always see some voltage fluctuation at the junction because of the thermal activation. But let's say we decrease the thermal energy at a certain level below a certain level so that there is no thermal activation is possible for the circuit. So do you understand? So in a scenario, normally when the thermal activation or thermal energy is there, we always have some fluctuation at the voltage at the junction. But when the whole system is cooled certain below temperature that there is no thermal activation or thermal noise is there. And then we need to lower the temperature, and we see that Cooper pair is forming and they create a macroscopic states, and there is no fluctuation in the voltage at the junction, at the Josephson junction. So because the whole system right now, the Cooper pairs, they are making the macroscopic state, and which can be described by a single quantum mechanical state. So there is no fluctuation in voltage at the Josephson junction. Now, when there is a certain quantum tunneling, so if there is a certain quantum tunneling in this junction, what we'll see that there is a slight fluctuation at the voltage for the voltage at the Josephson junction. So that means that this slight fluctuation in the voltage is not occurring due to the thermal fluctuation because we have already lowered the temperature. So thermal fluctuation is not possible. This is coming from the quantum mechanical tunneling, which is due to the Cooper pairs are tunneled, and this is involved that since this tunneling is not about a single particle, it involves a billions of Cooper pairs which are present in the superconductors. They involves in the tunneling, and this tunneling caused a measurable microscopic current or microscopic voltage change, which can be like from microvolt to millivolt to the junction, Josephson junction. Therefore, this tunneling object, the superconducting phase represent a collective degree of freedom of a macroscopic number of electrons. And that's why it is called as macroscopic quantum tunneling. So when it is a single electron, then you are talking about microscopic quantum tunneling, or when is a alpha particle, when is a single microscopic object. But since it's a Cooper pair, a whole system of Cooper pairs, there are large number of electrons are pairing inside the superconductor and they are tunneling through the junction. And this tunneling creates a macroscopic change in the voltage at the junction. So therefore, this tunneling effect is known as macroscopic quantum tunneling. And once we have this quantum mechanical tunneling predictions, and we can able to see these quantized levels, this can be also like in the electronic circuits. So therefore, that's why it is important that this Nobel Prize has been given for the two concepts. One is the macroscopic quantum tunneling, another is the energy quantization. It is shown in the electric circuit. And this phenomena is very much applicable for the quantum computation, quantum cryptography. So these have huge applications in real world scenario. And it also provided the fact that quantum mechanics is not only applicable to the microscopic world, but it could also be applicable to the macroscopic world. So guys, these are all for today's video. And if you want to join our interview guidance program, we regularly guide our students to prepare them for the PhD real interviews. So we prepare them with mock interviews. We provide guidance by one-to-one interaction directly to the students. And we also conduct a test series program for the NET and GATE. So please join these programs if you have requirement. And if you like this video, please share it and subscribe to the channel for more videos. Thank you so much.